ray-rllib has implementations of many reinforcement learning algorithms. The full list is available in this page, which we have seen before. Now, these algorithms have different learning behavior. For example, here are the evaluation graphs of DQN and PPO for the cardpole V1 problem. Orange is DQN and blue is PPO. It's quite clear from the graph that the learning behavior of these algorithms is different. We will first look at a learning metric called sample efficiency. And this gives us an indication of how much data the algorithm needs to learn. And this can be measured by looking at how many environment steps it took to reach a fixed level of performance. Let's choose this fixed level of performance to be the peak performance, which is a total reward of 500 per episode. And we find that the DQN algorithm reaches this peak performance after learning for 20K environment steps. In comparison, PPO needs roughly double the amount of environment steps to reach the same performance. So we say that DQN is more sample efficient and PPO is less sample efficient. Now, sample efficiency matters in two scenarios. The first scenario occurs when a simulation of the problem is not available and we need to train the algorithm on a real system, like the physical robot that we see here. In this case, stepping through the environment can be slow because we are bound by the speed of physical systems. It may take months to complete the reasonable number of steps required for learning. One way to work around the slowness is to parallelize, that is to run many instances of the environment simultaneously, thereby collecting more steps per unit time. But this is often quite expensive and prohibitive for physical systems. The second scenario occurs when we are using a simulation, but the simulation is based on real data. A stock market simulation for the purpose of trading is a good example of this scenario. Real data is often limited in size, so we only have a limited number of unique steps to learn from. For example, the stock market simulation might be based on 30 years of historical data because more data is simply not available. In both these scenarios, the environment step is the bottleneck, being either slow or limited. Therefore, we need to use an algorithm that can learn from the least amount of data. In other words, we should try sample-efficient algorithms first in these scenarios. Here are the 3 most recommended sample-efficient algorithms to try. However, keep in mind that DQN can only be used for problems with discrete action spaces. DD3 can be used only in continuous action spaces, while SAC can be used in both. Now, the ray-rllib algorithms page is the source for the action space requirements of an algorithm. So this page over here, and you see it says whether it supports discrete actions and continuous actions. So this is where I found out that DQN only works for discrete actions. So you go to the DQN row and see that it only works for discrete action and doesn't work for continuous ones. All right. Now let's look at another important learning metric called stability. Stability can be inferred by checking how wildly the algorithm performance swings over time. So DQN seems to have rapid oscillations during learning, while PPO seems to have a much smoother and steadier learning. Therefore, we say that PPO is a more stable algorithm and DQN is less stable. There are many problems where sample efficiency doesn't matter. This is especially true if we have a model-based computer simulation of the problem. All gym environments fall under this class. Since the simulation is based on computer models, they're typically fast, simulating months of real movements in mere minutes. They can be sped up even more by parallelizing. You simply need to run many instances of the environment to collect more environment steps. Random simulation initialization can ensure that unlimited unique steps are available for learning. So in this case, you should try a stable algorithm first, because they have a higher success rate in solving environments. The most important stable algorithm is PPO, which we have used extensively in this course. And it works in both discrete and continuous action spaces. This should be your go-to algorithm for all model-based simulations.